Hello friends, welcome to the introductory course on atomic structure and chemical bonding. This course is first of the two credit courses which are related to the core paper 1 in chemistry. The paper is titled as Atomic Structure, Bonding, General Organic Chemistry and Aliphatic Hydrocarbons. As the name suggests, in this course we will take up two topics, that is the atomic structure and chemical bonding. The rest of the topics will be taken up in the course titled Organic Chemistry 1, which will be offered separately. I am Dr. Sanjeev Kumar, Associate Professor in Physical Chemistry at the School of Sciences, IGNOU. I will be your instructor for this course on atomic structure and chemical bonding for the next 5 weeks. Of the 5 weeks, we would spend first 2 weeks on understanding the structure of atom, and over the next 3 weeks, we will learn about chemical bonding. In this course, we are going to follow a very different approach, what is called as the conceptual development approach, as against the typical descriptive approach. As the current understanding of the structure of atom is based on quantum mechanical approach, about which you have had a very brief exposure in your +2 chemistry. We would go a little deeper into the same. Instead of stating the concepts that led to the quantum mechanical ideas, we would gradually build up on their understanding and put them in perspective. Accordingly, our strategy to understand the structure of atom would be as follows, that is, we will talk about why of quantum mechanics to begin with, then we will talk about what is quantum mechanics. Then we will see that how does wave mechanics, that is one of the approaches of quantum mechanics, that works or operates. And in the process, we will learn about the quantum or the wave mechanical treatment of hydrogen atom, and in the process, we will understand what is an atom, how does it look like, and things like that. We would spend first 2 sessions on establishing the inadequacy of classical mechanics, and then in the process we will try to establish the need for a new theory. In this context, we will then bring in the concept of quantization and discuss its success. Thereafter, we will briefly discuss the Schrodinger's wave mechanical formalism and show its applications, and in this process we will learn about the quantum mechanical description of atomic structure. And on the other hand, in the context of chemical bonding, we would begin by giving a historical perspective of the developments of the ideas of chemical bonding. We would then explain the classical theories of chemical bonding and outline their limitations. This would be followed by a detailed account of the modern theories, that is the valence bond theory and molecular orbital theory. After that, we will take up bonding in metals as a separate case separately, because it involves the bonding of exceedingly large number of atoms, because typically when we talk about bonding in other cases, we will be talking about a very small number of atoms there, but in case of metals, a large number of atoms are involved in the bonding. And in the last week, towards the end of the course, we will take up ionic solids in terms of the bonding, their structure and energetics of their formation. We would also take up weak interactions, that weak interactions between molecules and ions and things like that, before concluding with the energetics of dissolution. Let's begin the discussion on atomic structure by the first lecture attempting to establish the inadequacy of classical mechanics in dealing with microscopic systems. The lecture plan for today's session happens to be as follows. That is, we will first look at what is the basic premise of classical mechanics. That is, what is classical mechanics, what does it do, and how does it serve our purpose. Thereafter, we will see that what kind of experiments are there which pose challenge to classical mechanics. That is, there are certain experiments which could not be answered or could not be explained on the basis of classical mechanics. We will try to have a look at them. And in this process, I will take up 2 such important experiments that happen to be Blackbody radiation and photoelectric effect in today's session. I will try to see what were the experiments, what kind of results were obtained, and what were the classical predictions for those experiments, and how the two were mismatching. So in this process, we will try to see that our classical mechanics is inadequate to explain these results. And then towards the end, we will try to sum up what we learned in today's session. Okay, let's make a beginning. Let's make a beginning by looking at what is classical mechanics. Actually, if you really ask me, Classical mechanics is a set of laws that have been formulated on the basis of our observation of nature over a period of centuries altogether. That means whatever we gathered in terms of looking at the motion of kind of astronomical bodies, sun, moon, and things around us. So we see things in macroscopic world, and all those observations have been documented or formulated in terms of certain laws. And the three basic pillars of classical mechanics are the Newton's laws of motion, the gravitational law, and Maxwell equation. These three put together put a classical mechanics on a very strong foundation. And on the basis of these, practically most of the things we know of in the macroscopic world could be explained. Now, if that be so, let's take some examples now. Let's see how do we put classical mechanics into use. I'm sure that these pictures will be quite illustrative to you. The first picture here talks about a baseball game. The same thing happens in case of women cricket as well. So what we see here is the player has shot the ball, and the fielder here is trying to assess, ascertain where the ball is going to fall so that he can anticipate the catch and take it. Same thing happens in cricket as well. Now in this case, we are not making any calculations per se, but we are doing some kind of a mental calculation. We see, okay, how is it going, how high is it going, where is it going to fall. So we anticipate and position ourselves to make the catch. Okay, so that is a kind of mental calculation, but all that again are based on our understanding of classical mechanics. Okay, this is one aspect of it. Now here what we see is, this is a typical picture. I'm sure that most of you would have come across this picture. This is trying to predict. Suppose the ball had hit with, because now we know the instrumentation is available now, and the moment the ball leaves the baller, we can work out at what stage has it gone, what is the force on that, where is it going to fall, where is it going to land up eventually thereafter. That is, whether it's going to hit the stumps or not. So that can be predicted fairly well, and then we believe in the outcome of such kind of predictions. And even same thing happens in case of tennis as well. So there are three instances. From sports we know that we can put classical mechanics to use, and then we have reasonably good faith on the outcome of such predictions. We can take certain more examples. We know that in rocket science, when we launch rockets or a satellite going up, we know precisely when to plan all the events which are going to take place in the process of launch of satellite to its establishment in the orbit. Everything is well planned, precisely in terms of time, what is going to happen at what height, at what time, and so on and so forth. Okay, so this all is possible because we know our classical mechanics laws are perfectly predictable, perfectly useful. Similarly, we can even predict the cosmic events, like when are we going to have a meteor shower. We can predict it, and we actually see, we can go rooftop and then actually enjoy that thing, because it happens the way it has been predicted, because we know how things are going to happen in time. Now that is as regards our the validity, so to say, of classical mechanics. Towards the end of 19th century, that is around 1890s and things like that, people thought, people in physics particularly thought, there's nothing left in physics, because they were so contented with the success of classical mechanics that practically anything which you come across we can explain fairly well. The only thing probably physicists were doing at that point of time was to see that if I can make measurements slightly more accurate. For example, if I have a table, if I measure its length, say it's about 1.7 meters, maybe I can use a different scale and make it, okay, I can measure it to 1.73 meters, or maybe 7.32 meters, or maybe I can go even further down. That means I am just looking forward to an extra decimal place. That means there's nothing new to happen. Only thing is I'm trying to get more and more accurate measurement, and that's not very, very significant. So people thought that nothing is left in physics, to the extent even that a physicist by the name Philip von Joly actually advised Max Planck not to pursue physics, because there's nothing what he could expect from physics to happen at that point of time. And fortunately for us, that Max Planck doesn't listen to him, because it is Max Planck who actually gave us the quantization concept and the quantum mechanics as we know of today. Okay, now in the backdrop of such a scenario that everything is predictable, there were certain experiments. The experimental findings were such which posed challenge to this established kind of a branch of science, domain of science, that is classical mechanics. There are 5 significant challenges: the blackbody radiation, photoelectric effect, anomalous heat capacity of solids, atomic line spectra, and Compton scattering. In fact, the last one, the 5th one, actually is not a challenge per se, but I am clubbing it here because this also could not be explained on the basis of classical mechanics. In fact, Compton scattering was used to kind of verify the photon concept given by Einstein. We will come to that later on, maybe in the next session we will talk about it. And out of these 5 experiments I am listing here, in today's session I will try to discuss about the first 2 of them in little more details. We will see what are the experiment, what are these systems, what kind of results are obtained, and then where does classical mechanics falter in explaining them. Okay, let us make a beginning with the first experiment, that is blackbody radiation. To come to blackbody radiation, let us understand that we know that anything which is hot emits radiation. I am sure that you would have experienced while sitting close to a fireplace that heat comes to you in the form of a radiation. And also we would have seen, if you visited a blacksmith, you would have seen as the blacksmith goes on heating the iron rod to higher and higher temperature, the color of iron rod changes. It is a general phenomenon that anything which is hot is going to emit radiation, and the nature of radiation which comes from hot object will depend on 2 things: 1, the temperature, and 2, the nature of the material being talked about. Now, this is just a small listing over here. What we see is that when the temperature is low, say around room temperature or so, or my body temperature for that matter, we emit what is called as IR radiation. And as the temperature goes up, we see that the color becomes cherry red. If it becomes about 1000 degrees centigrade, it becomes yellowish. At higher temperature, it becomes white, and even beyond 2000 degrees centigrade, maybe we can expect UV radiations coming from the hot object. So, what you see is that the output from a hot object depends on the temperature. And I am sure that you would have come across this ear thermometers nowadays being used, especially for children. The basic principle of this thermometer is that when you insert that probe into the ear of the child, because the body of the child is emitting, the child has fever, the temperature is more than the normal this thing. So, the IR radiations which come, that will be sensed by the sensor of the thermometer, and that will display it as a reading on the thermometer. That is a purely a very convenient proposition, and this device has been created by NASA for different purposes there, but it is put to common use nowadays. Now, let us come to what is blackbody. Blackbody actually is an ideal system, and I am sure that we all know that nothing ideal exists per se. Ideal are systems which do not exist on their own, but we can come to a close approximation to them. And a blackbody by definition is a body which absorbs all radiations which fall on it, and in turn when heated emit all radiations out of it. Let us take an approximation of that. Now, suppose I have a hollow sphere, say I have a sphere which is empty from inside, it is hollow, and I make a small pinhole in that. When I have that, then any radiation, so this is just depiction of that, suppose some radiation gets into this pinhole. So, once this gets in, the radiation will go strike the wall opposite to it and get reflected inside, and then this radiation which has gone into the sphere will get reflected repeatedly, and eventually it will get absorbed there. No matter what is the kind of radiation I am throwing on that, that will get absorbed. So, in principle what we can say is such a body is a perfect absorber. It absorbs all radiations falling on that. And if I heat it in turn, when the radiations come out of the blackbody, come out of such a body, that will be giving all possible radiations. So, such a body which is a perfect absorber as well as a perfect emitter is called as a blackbody. So, the radiation which come from such a body is called as blackbody radiation. Let us try to see what are the results we obtain in case of blackbody radiation. There are 3 very crucial results what we obtain. The first one is, as the temperature of blackbody increases, what we find the amount of radiation coming off increases. That is, this gives you some measure of the intensity or energy density, because this axis is energy density. That means amount of energy coming out as a per unit wavelength. So, on this axis we have got wavelength, and this axis is energy emitted or energy density, energy emitted per unit wavelength. Okay. So, what you find is that as the temperature increases, we find that say from 35 degree, 100 degree centigrade Kelvin to 4000 to 4500 and so on and so forth, as temperature is being increased, we find the energy output is more and more. That means you can see it in terms of area under these curves. The area under these curves goes and increases. That is the first observation. The second observation here is, as the temperature increases, we find say at a given temperature 3500 K, what we find is that this is the kind of distribution we have. At this particular wavelength, there is a maximum energy coming off. As we increase temperature, we find that this maxima shifts to these sides. What we see is a trend of this kind. That is, as temperature is increasing, our maxima shift to a lower wavelength. That is something what we observed in case of blacksmith's example. That means when the iron rod was heated more and more, the color changes. That is, the outcome, that is the maximum wavelength which is coming out, is different over there. And the third most crucial observation here is, the spectrum depends on temperature and not on the nature of object. That means what is the black body made up of doesn't matter. The only thing is the outcome will depend on the temperature of the black body. So this is in contrast to what we had in case of a general observation. That is, the energy output will depend on the nature as well as the temperature of the body. So that's a basic difference over here. Now, classically speaking, there are certain observations we have to see how do we reconcile with what we experimentally observe. There are three important things here again. First is your Stephen's law. Stephen's law, proposed initially by Stephens, later on modified by Boltzmann, or also called as Boltzmann-Stephens law. What it says is, the rate of emission of radiation energy from a surface of hot object is proportional to the fourth power of the temperature, that is absolute temperature. And what happens is, we have the output coming here is proportional to T4, and that actually explains our first observation in a way that accounts for the first observation, that as temperature increases, the energy output is increasing. Second important law is what's called as Wiens Displacement Law. What it says is, the lambda max of the wavelength distribution shifts to lower wavelengths as temperature increases. What it says is, the lambda max into T is a constant. That means if T goes up, lambda max has to come down, and this explains the shift in the wavelength maximum of the emission. So the two observations are there broadly. That means qualitatively speaking, okay, there will be increase, we find an increase there. There will be a shift in lambda max, that also we are explaining. When we try to explain the energy distribution curve, the whole curve as such, in terms of using Stephen-Boltzmann law and modifying that further, he gave an expression which shows that E lambda, that is energy emitted at a given wavelength, is proportional to lambda 5 and so on and so forth. This agreed to a good extent with the experimental observation. What you find is that these dots are our experimental points, and this dotted line here gives you the prediction from Wiens law, and we find that for lower wavelength, Wiens explanation matches with the experiment, whereas for high wavelengths there is a discrepancy over there. Next serious effort was made by Lord Rayleigh and later on modified slightly by Jeans. And what Lord Rayleigh said was, the black body, he assumed the black body to be a collection of oscillators. That means the atoms and molecules constituting the object or the black body is visualized as an oscillator over there that can absorb EM radiation of all possible frequencies. That is, you talk about classical mechanics, energy is continuous. And then second assumption was, total energy which is available to a system, that is distributed amongst all possible oscillators in the system. So on the basis of these two assumptions, Lord Rayleigh proposed the following expression, formulated the following expression, and this expression was in reasonable agreement vis-a-vis the high wavelength region of the spectrum what we got in case of black body radiation. We find that for the higher wavelength region here, there is a agreement between experiment and theory. This is your curve from Lord Rayleigh's prediction, and these are your experimental curves. But whereas for the lower wavelength region, there is a mismatch over there. So we find that Wiens law explains the lower wavelength region, Lord Rayleigh's proposition explains the high wavelength region, but none of the two gives you the whole curve. That means our classical attempts to explain black body radiation happen to be inadequate. So we find that predictions of classical mechanics are not in agreement with experiment, and we find that classical mechanics is inadequate to explain our black body radiation, and we need something different from this mechanics now. And such an explanation of the phenomenon was given by Max Planck in year 1900, about which we will talk maybe in the third episode. Now, let's move on to the second experiment I mentioned earlier, which I want to take up for today, that is the photoelectric effect. Another very, very important experiment which posed a serious challenge to classical mechanics. The experiment is as follows. Suppose I take certain metal, a soft metal like cesium or so, and if I throw some light on that, what we observe is that when light falls on that, it emits electrons from this metal, and if I go on throwing light, electrons keep coming off the mirror, and the electrons which are coming out constitute current. So, such an effect whereas you are getting electrical current as a consequence of light is called as photoelectric effect, and the electrons which are emitted because of light are called as photoelectrons. Okay. So, that is the kind of phenomenon I am talking about. Now, what's important is that when this experiment was studied somewhere around 1887, what we found was that there are a few important observations. The first observation, significant one, was that is the moment you throw light, you find a current coming over there. The moment switch off the light, there is no current. That means this emission of electrons from the metal is instantaneous. There is no time lag between the light falling on the metal and electrons coming from there. That is the first and significant observation. Second observation was that if I throw light of a certain wavelength, say a certain low frequency this thing, we find that there is no electron coming out. I increase the frequency slightly, we find that still there is no current coming. Increase the frequency further, we find okay, now the current starts coming. That means electrons need certain, that means the metal needs certain minimum amount of frequency of the radiation for electrons to be emitted from there. If I go on increasing frequency, we find that electrons keep coming, that means the current keeps flowing, but the electrons which come off, they are of higher kinetic energy. We need, there is something called as stopping potential, which physicists typically talk about. That means that is how the experiment was designed. That means we try to increase potential so that we do not let the electrons come off. That is called as stopping potential, and stopping potential actually is a measure of the kinetic energy of electrons coming off. But for us, it suffices to know that we need a minimum amount of frequency for the radiation to electrons, for the electrons to be coming out from the metal. That is called as a threshold frequency. That is the second observation. The third one was, as I just mentioned, that if I keep on increasing frequency, okay, let us say this is the kinetic energy of electrons, where I am trying to increase frequency over there. So, what you see is, as the frequency is very low, we can see that there is no current, there is no current coming over there. As you go on increasing frequency, we come to certain value nu naught. At this stage, electrons start coming off. As we increase the frequency further, we find that electrons keep coming and they have more and more kinetic energy as we proceed further. So, we find that the kinetic energy of the emitted photoelectrons increase with the frequency. That is the third observation we have. And then the fourth observation was that if I have the same metal and I increase the intensity of radiation which is falling on that, what is observed thereafter is that the current continues to be there, but the current, the intensity of the current or the magnitude of current increases. That means with increase in intensity, there is more current coming there. At the same time, the stopping potential of these electrons remain the same. That means all these electrons which come off, they come out with the same kinetic energy. That is the fourth observation we have. So, let us see what are the four things we have seen there. The photo emission is instantaneous, that is there is no time lag. A minimum frequencies, that is called as a threshold frequency, is required. Thirdly, the kinetic energy of the emitted photoelectrons increase with frequency, and lastly, increasing intensity increases the number of electrons, but their kinetic energy does not change. So, there are four significant observations vis-a-vis our experiment of photoelectric effect. Let us see what classical mechanics tells us on these. The classical predictions, let us take one by one all of these. The first is that classically speaking, our radiation is existing as a wave, okay, and the energy of this radiation is distributed over the whole wave. So, we have a small electron target over there. So what classical mechanics says is, we have a small target, say electron over here. This is wave coming there. Okay. Now what it says is, this wave is coming with certain amount of energy. This electron needs certain energy to come off from there. So as this wave is coming, this keeps on absorbing energy. When sufficient amount of energy comes to this, it will come off. That means the electron should not be knocked off immediately. It should come out after certain amount of time. There should be a time lag according to classical mechanics. That is the first observation or first prediction of classical mechanics is that there must be a time lag between throwing the light on the metal and electrons coming from there. But we remember that experimentally we observed just the opposite of that. Second prediction. Now second prediction is that since we have the electron and my radiation is coming, the classical mechanics presumes or suggests that no matter what energy, what wavelength I take, what frequency I take, as long as, suppose I take say a low frequency radiation. So low frequency means it's a high wavelength radiation coming there, energy is low, it's coming there, it gets absorbed to a certain extent. Maybe I have to pass this radiation for a long time, and when enough energy is there, it will come off. If I take higher energy one, it will come out faster, that's all. The only thing is, there is no need for any threshold frequency. That means the electron should come out irrespective of what is the wavelength or what is the frequency of radiations used for the purpose. That is the second prediction from our classical mechanics, again in contradiction with the experimental observation. Thirdly, if I increase the amplitude, that means if I increase the intensity, basically I am increasing the amplitude. What it means is, a higher intensity radiation means what? Higher intensity radiation means that intensity, this radiation has got a higher amplitude. Let's take an example. Now suppose you are standing near the seashore, a small wave comes, a ripple comes, it just comes, hits you, and that's all, matter ends thereafter, nothing happens to you. But as against that, suppose a large wave comes, with large amplitude, or there's a lot of energy in that can even knock you off the feet. Okay, so you'll be thrown off from the seashore. So that is what exactly is expected from our this phenomenon over here. If I increase intensity, what is expected is that if a high intensity radiation is coming, the electron will be knocked off and it will have high kinetic energy. Whereas what we experimentally observed was that the kinetic energy of electrons, when it came off on increasing the intensity, had no change. It came out with the same kinetic energy, because and the kinetic energy depended only on the frequency of radiation and not on the intensity. So let's again see what we experimentally observed and what is classical prediction over there. Experimentally observed, there is no time lag. Classical prediction is there must be a time lag. Second experimental observation was that we need a minimum frequency called as threshold frequency. Classical prediction does not look forward to any threshold frequency. Thirdly, the kinetic energy of the emitted photon increases with frequency, whereas classical prediction is that kinetic energy should depend on intensity and not on frequency. And fourthly, increasing intensity increases number of electrons, but kinetic energy remains the same, whereas classical prediction is the increase in intensity should give faster electrons and not more electrons. So we find that all the four counts, experimental observations and the classical predictions, do not match. That is the second instance we are saying, and what we find from here is that the predictions from classical mechanics are not in agreement with the experiment. That is, or in other words, we can say the classical mechanics is inadequate to explain the results of photoelectric effect. And a successful explanation of photoelectric effect was given by Albert Einstein in 1905. Let's sum up what we've done today. What we've done today is we started with understanding what is the basic premise of classical mechanics, and on the basis of that, how comfortable we are in explaining the macroscopic observations what we have with us. And thereafter, having established that classical mechanics works fairly well for macroscopic system, we came down to two experiments particularly, one Blackbody radiation and two a photoelectric effect. And on the basis of these two experiments, we have been able to see that the experimental observations what we had and the theoretical predictions from classical mechanics do not match. That means the classical mechanics happens to be inadequate in explaining the results of these experiments. In my next episode, I'll take up three more cases. One is that of anomalous heat capacity of solids. second is atomic line spectrum, and thirdly Compton effect, to re-emphasize this assertion of mine that classical mechanics is inadequate in explaining certain experimental phenomenon. And once having done that, in the later session we will try to find out a solution to this. That means we will bring in the concept of quantization and see how does this get over this inadequacy of classical mechanics and does explain all these results fairly well.